A regular expression is a pattern describing incoming text, and the most abundant pattern in most text is cycles or repetitions. Repetition of words, letters, digits, and sometimes even whole sentences is a common feature of text. The pattern describing such text should be able to describe these contained repetitions as well. In practical usage, repetition handling is the defining feature of regular expressions, and you would hardly find any important regular expression without it. Repetition can take many shapes and forms, in addition to ones mentioned earlier. Now, when I say repetition of letters or digits, I can mean repetition of a single character like M or Z, repeating in or Z, or in case of numbers, we can say 666. But I can also mean a sequence of letters or digits repeating multiple times. So in say hello 123, you would see we have alphabets repeating 5 times, followed by numeric digits repeating 3 times. Say in a phone number, we would say a fixed number of digits must repeat to make a valid phone number. Like near the end, you would see a sequence of numbers appearing 3 times and then a character separator followed by a sequence of number appearing 4 times. Not the same kind of repetition as the same number repeating multiple times like 666. All of these repetitions can be captured in a concise way in regular expressions using a concept called quantifiers. This is the topic of today's video in our regular expression series. I am Ali from Learn Awesome. Let's go over its formal definition and then explore supported quantifiers for various scenarios. So a quantifier after an element such as token, character, or group specifies how many times the preceding element is allowed to repeat. Nothing fancy to it, right? Pretty straightforward concept. However, I would definitely like to emphasize the earlier part of this statement more than the later. Quantifiers are not character specific. They can be applied to any repeating thing or constructs in regular expressions. You saw example of some of these in previous slide, but some of the constructs haven't been introduced yet and won't be in this video. I'm emphasizing this point repeatedly as I would be using basic examples in introductory video in the beginning, but don't let it mislead you. You can think of such elements as x in algebra. You start to learn with x as a number in start, but later it turns out x can be substituted with an entire equation. The element in our definitions is like x. Now let's put that thought in code storage for now and move on from here. So this is the list of commonly used quantifiers in regular expressions. You may have seen some of those in earlier videos in regular expression series on this channel, but we shall go over each of them one by one to solidify our understanding. Let's begin with the first one. Question mark or optional is perhaps the most basic quantifier and is used to define repetition of an element exactly 0 or 1 times. This is why it is sometimes called optional because absence of that element is perfectly okay here. The best example of its usage is color or color with a U. For those unfamiliar with this English word is written differently in US versus British English. Words like color, favorite, and flavor are without the character U in US English, but in British English, the presence of U is required as correct spelling. So if you are looking for these words in an input sentence or documents via regex, you need to take into account both variants. And what better way to do so than use our question mark or optional quantifier, which treats absence of U as valid and presence one and only once as also a valid match, 0 or 1. I hope this is clear with these three examples on the screen. Next is the enhanced model of optional, that is Asterisk or Kleene star, which matches 0 or more repetitions of an element. More here means unlimited. So let's say a character repeating indefinitely would be matched against a steric symbol in regular expression. Also known as Kleene star after mathematician Stephen Kleene, with great contributions to finite automata, recursion, and regular expression theories. Considered founder of regular expressions and having great contributions towards computer science, this and Kleene Plus quantifier are named after him. Don't beat yourself up if you never heard of him. I hadn't either until I researched what Kleene star means for this video. Moving past Stephen Kleene with a thank you note, the important thing to remember about this quantifier is that, like optional, this does allow 0 matches. So absence of preceding element is a valid match. So using examples from previous slide, color, favorite, and flavor would match successfully if we replace question mark with asterisk. However, it would start matching color with 0, 2, 20, or 200 repeating U characters after COLO and before R. So let's stick with question mark for these and consider X** as our regular expression, which would match an empty string X, XXXX, and ABCD. Last one as ABCD has no X, which is okay because it allows for 0 repetitions. Similarly, XY* would match X, XY, XYYY, but not ABCD since presence of preceding X is mandatory here. Just to make sure there is no gap in understanding, XY*Z would match XZ, XYZ, and XYYYYZ, but not X or Z alone. Let's now introduce plus, Kleene plus. It's the next step in evolution of quantifiers. It's pretty much same as Kleene star except that instead of 0 or more repetitions, it requires preceding character to appear at least one or more times. At least one is the key point here, which means absence of preceding element would result in unsuccessful match. So X plus would match X, XX, XXXXX, but not ABCD, unlike X star. Similarly, X plus would match AX, AXXX, and XY plus Z would match XYZ, XYYYYZ, but not XZ or X or Z. So far, we have been playing with 0 or unlimited, 1 or unlimited, 0 or 1 repetitions. But our bounded repetition quantifier changes the game, giving you full control of number of allowed repetitions with a catch that it strictly enforces a specific number of repetitions like 3 or 4. So say in a date, you would enforce a limit of 4 numbers to represent the year. More simply, A curly braces 3 would match AAA but not AA or AAAA. The syntax of these custom repetition quantifiers is a bit different, where quantifier is curly braces containing the number of repetitions. As for the last example on the slide, note that \d is a legit shorthand for digits 0 to 9. So \d in curly braces 3 would mean any 3-digit number would be considered a match and anything else would not be a match. A lower bounded repetition quantifier allows you to control the minimum number of required repetitions and allows for unlimited number of maximum repetitions. So you can write Kleene star as curly braces 0, comma, and Kleene plus as curly braces 1, comma, using this notation. It only enforces limit on minimum repetitions. So A curly braces 2, comma, would match AA, AAAA, AAAA, but not A. Similarly, A curly braces 2, comma, wouldn't match A in candy, but would match A's in candy and candy. Upper bounded repetition is opposite of previous one as it enforces limit on maximum number of repetitions only. So it can be read like 0 or max repetitions allowed. Note carefully, it is severely restricted in acceptance across languages and parsers, so it would work with some but not most of the parsing engines. Before using, always check if the language or parser you are using even supports that before using, and I would strongly adjust to avoid it unless necessary and you don't have a workaround. If you do end up using it, the syntax is pretty much the same as others like A, curly braces, comma 3, which match A, AA, and AAA, but not AAAA or any other further repetitions. The most precise control for range quantifiers come in form of min-max quantifier where you can define both the lower and upper bound of its range. You can control whether it repeats at minimum 0 or 1 or 4 and 10, 15 or 20 times max. In addition to straightforward example of A 3, 5, which would make AAA, AAAA, and AAAA match and nothing else. I also included a rather complicated example of matching an IP version 4 address, but before we go to it, let's understand two concepts called meta characters and groupings in context of quantifiers, since they would be used in that example. So let me quickly get over a concept since it confuses many people, especially in the start, and this is how we distinguish between matching multiple characters using quantifiers like steric, plus, and question mark, and normal characters steric, plus, and question mark. Both look the same, but when used in regular expressions, these characters have a special meaning. So what if I just want to match plus character rather than using it as a quantifier? Well, before diving into solution, let me first introduce you to the term meta character, which essentially means a character with special meanings or significance. The quantifier symbols are all examples of meta characters. And to use such characters literally, the fix is to simply put a backslash behind a meta character. And it is stripped off of its special meaning and status and becomes an ordinary character which you can match to plus or question mark characters in input string. Regular expressions are weird in the sense that just like you make meta characters into regular characters by using backslash prefix, you can also transform some characters to meta characters using backslash as well. Examples are backslash d, which means 0 to 9 digit, not the character d, or backslash w, which means a word, or backslash b, which is a word boundary, and backslash s, which is space. You will learn some of these with practice and example, but just remember, whenever you see a backslash appearing in regular expression, do remember it is being used to transform a meta character to character or otherwise. So if you recall in beginning of the video, I told you the preceding element of quantifier is just like x in algebra and can be more than a character. Well, groupings is what I meant by that. They can be a bunch of regex constructs and quantifiers can be applied on them. Taking one such example, if I enclose a word in parentheses and apply a quantifier on it, for example, stop enclosed in parentheses followed by curly braces 1, 3, it would capture stop, 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 or stop, stop, stop in the input string, the entire word repeating 1 or 3 times. Taking another example, a more restricted form is ho enclosed in parentheses followed by 3 in curly braces, which would require the word to be repeated exactly 3 times, like ho 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 by Santa Claus, where it wouldn't make any sense to repeat it any other way. Note that what is enclosed in parentheses can be more than just a word and can be a regex sub-expression. With that settled, let's move on to the IPv4 example. Does that look complicated? Well, cause it is. But we are not gonna stick with kid examples forever, right? If you want, there were plenty on the previous slides, but to work with regular expressions like a pro, you need to brave a bit complicated ones as well. So let's understand it. In case you're not familiar, an IPv4 address is a networking address of computers over the internet of the type 192.168.15.2 or something like that, like 4 numbers separated by dots. So our expression starts with a cap sign, which is input boundary assertion, meaning the input string must start with a match to our following expression. So next here we have a non-capturing group, which means a group which we don't intend to use later in regular expression, and its sub-expression says backslash t curly braces 1, 3, which means any single digit number that appears 1 to 3 times. Backslash d can match any number between 0 to 9. Backslash d 1, 3 is a shorthand for any 1 to 3 digit number like 473, 196, etc., but not 1024 since it's 4 digit. Similarly, a number must appear since lower bound is 1 here. So we are definitely expecting a number. This is followed by a backslash dot. If you recall from earlier videos, and I'll reiterate for new viewers, dot is a wildcard character. We are using it as a literal character dot or decimal point or period here. To do that, we need to tell regular expression engine that we don't intend to use it as a wildcard, but as a regular character. And to do so, we need to convert it from a meta character to a character, and we do so by prefixing it with a backslash, which changes its meaning to a normal dot character symbol, stripping off its special status. Okay, so our expression in this group in total would match three-digit numbers followed by a dot character. With our example input string, this portion until here is gonna match 192.168.2 dot. What is left now is the last number in our IPv4 address, which is 15. For that, we simply have a final capturing expression in place, which is backslash t 1, 3, which means any 3-digit number which includes the two-digit number 15. So it will capture the 15 part, and dollar would ensure that the input string ends here and no more characters follow. With this, we can finally declare 192.168.2.15 as a match to our IPv4 regular expression. Note that this would also match unacceptable addresses like 1024.168.1.1 because IPv4 numbers cannot exceed 255. But ensuring a number range is much more involved as regular expressions consider each digit individually, and ensuring a numeric 0 to 255 range would sidetrack us from our goal of understanding quantifiers a lot. So we won't go that far in this one, maybe in a later video where we discuss practical regular expression examples. Okay, so with that head spinning example in our rear view mirror, let's go over some simpler ones to solidify our understanding so far. But remember, we are not finished with quantifiers yet, just trying to solidify what we learned up till now before moving ahead. So I have listed a bunch of examples to try here. Let's try them all in our test website like Regex 101. Right, so our first example is trying to come up with a regex that would find all words starting with A and ending with F. So let's first write some examples. So I would say Ashraf was aloof from the world just like Adolf. Okay, and now we are going to write our regular expression. So first of all, we need to come up with a word boundary. Backslash v, if you recall from our assertions video, stands for the defines the word boundary. So if I write backslash v, it's gonna detect the start of a word, just like here, and then I type a, it detects the first character, and then I'm going to use backslash w. It matches any word character, which is any character between a to z, capital A to z, 0 to 9, or underscore. And next I'm going to use the Kleene star or steric quantifier, which is going to match all the way until end of the character. And then I'm going to write F, complete the match, because we are trying to find words which start with A and end with F. All right, so it found the first word, but we have many others which it's not finding, and the reason is the global flag is not turned on, so it stopped after first match, which you don't want it to do. So turning on the global flag, it finds all three words from our example sentence. Okay, our second example is finding all words in sentence that are 2 to 6 letters. All right, so let's go back. So we can use the example input listed there, or we can do it right over here. So what I'm going to do is I'm going to say after W, I'm going to use the min-max quantifier this time. And since we are trying to find 2 to 6 letter words, I'm going to specify that. And there's something not right. Oh, sorry, I forgot to remove this A. That's the problem with paste. Okay, this kind of selected almost anything, so let's make it short. Okay, this is to make this work properly, let's also end it with a word boundary. So now it's working fine. So if I do it for, it should also include from. Yes, and now the word should be included if I do 5. Yes, so this is working perfectly. Next up, we have find all words that start with Java. So I'm going to change it and say JavaScript is not Java. And in here, I'm going to say Java backslash W static. And it's going to find both matches. And why did it work? Because static is a 0 or more matches. So it's gonna match here even if there's nothing appearing after Java, and it's gonna match the entire script part here because static can go unlimited. Okay, our next simple example is find all dates in m-d-yyyy or mm-dd-yyyy format. So let's go back and give it a try. Let's come up with an arbitrary date, and now we are gonna say \t for digit, and I'm going to say 1 comma dash \t 1 comma and then dash \t 4, because year must be a 4-digit number. In fact, this is a bit misleading because it's also going to match 35555, so we need to impose a limit of 2 here, and now it's fine. And similarly here. And now it's a good example of expression. Again, we are not going into uh, doing the range thing in this video because that would take a lot of time. Okay, the last is find person or undead person in the sentence, right? So the phrase an undead person is still a person, right? So we need to find both of these here. So I'm going to say an undead person is still a person, and we need to find both in this sentence. So to do that, I'm going to say in parentheses undead, and now I'm going to use the optional quantifier here, the question mark one, and then the person, undead space. All right, and as you can see, it found both. One match is here for the undead person, and the other one for the person one. Had fun with simpler examples? Get ready for another head spinner. This time a phone number matcher. So let's go over this one. So again, the cap sign enforces start of input string as assertion, followed by the first group in parentheses, which expects a plus sign, which means the following would be a 1 or 2 digit country code, like this one. So here again, since plus is a special regex meta character, which means clean plus quantifier, we have to prefix it with a backslash to strip off its special status and make it just a regular character match. So the sub expression is expecting a plus sign following by a 1 to 2 digit country code, which is a digital number. So \t 1 to 2 digit maximum. And after that, we expect a space to appear. So space is specified in regular expressions using \s. So \s would match any space that exists here. Now here's the fun part. When telling your phone number within your own country, you don't include the country code. You just specify this part, right? The country code is understood and therefore unnecessary. So depending on context, the entire country code group is optional. And when we use the word optional, we have a friend, the question mark, or optional symbol to help us here. So this entire group is suffixed by this question mark to indicate its presence is optional. If it's there, good. If not, no worry. But if the phone number in input string starts with plus, then this group would kick in to ensure a match, as rest of regular expression won't match that part, and entire match would fail otherwise. Okay, next is the 3-digit mobile carrier code right here. So mobile carrier codes are generally 3 digits and are enclosed in, again, optional parentheses. And note this time the parentheses in regular expressions are prefixed with backslash to strip off their special meaning as a meta character in regular expression, ensuring they are treated as a regular character match and not start of a group symbol. One thing I'll clarify is that mobile carrier codes are 3 digit, and this regular expression is for mobile number match. Landline numbers have city codes which are usually 2 or 3 digits. So if you want to use this regular expression in your code, update this part 1 to 2 or 1 to 3 here. Okay, now the mobile carrier or city code followed by the 7-digit personal number is broken down into 3 and 4 digit parts, and they are separated by either space, dot, or dash, depending on culture and countries. And there's no strict rule here. All three are valid separators in a full number. So for such cases, the regular expressions have a special syntax where you enclose all options in square brackets. So backslash s dot and dash means either space dot or dash from input string. Backslash s being a special shortcut for space. So here again we enforce 3 and 4 digit separation using quantifiers here and here. I hope with these two awesome examples of IPv4 and phone number, you won't be intimidated by scary looking regular expressions ever again. Another very important characteristic of quantifiers is active versus lazy behavior, which you can control. By default, all quantifiers we discussed above are greedy or active, that is, they would consume as many matching characters in input string as possible by default. So a regex of asterisk would match a string a without blinking. This can all change if you suffix them with a question mark, which basically is an instruction to change quantifier mode to non-greedy or lazy or reluctant. So A static would match the entire string A, matching all 5 characters A. But A static question mark wouldn't match a single A in A, because A static means 0 or more matches. So it would settle at 0 matches. Same goes for A question versus A question, where former would match first A of, let's say, A, but second would fall back to 0 match allowance, just like A static. In case of A plus, since at least one match is necessary, A plus would match all 5 A's in A, but A plus question mark would stop at first A. Just adding a question mark would turn an aggressive matcher into a lazy, foot-dragging, lethargic one, which wouldn't want to match a single character unless forced to. Unless forced to, well, the important point is it would only match more characters if it's impossible to match rest of the pattern with fewer repetitions. To understand this statement, let's see behavior of a static question mark b and input string a b. Now, even though question mark is present, it would match all 6 A's, as regular expression only matches if all A's and at least one B is matched. Same goes for A static question mark dollar, like this, and A, which would force regular expression to match all A's, since it's impossible to match regular expression without matching all A's. If I remove the dollar part, you see nothing is matched. Even for greedy algorithms, they would try fewer repetitions if it's otherwise impossible to match rest of the pattern. Consider example regular expression A pipe B pipe C plus. Let me show you. A pipe B pipe C plus and input string ABC. The group would happily and greedily consume the entire string and evaluates to C. However, if I change regular expression to ABC plus C, then it would first greedily consume the entire ABC, but since the regular expression can't match rest of the pattern, the quantifier is reduced to consuming A and B only, evaluating the group to B. Active and lazy have kind of same and opposite behavior with respect to parser. One would eat entire match aggressively and then during backtracking give up characters one by one for greater good. That is giving priority to matching even if it has to give up what it has consumed. Lazy, on the other hand, does not want to consume a single character, but would reluctantly do so during backtracking for the greater good. That is, giving priority to matching even if it has to eat more characters. If both last sentences sound the same, that's because they pretty much are. They put an equal amount of strain on the parser in their own way. The possessive flavor, which is supported in limited languages, is a greedy plus version and is activated by adding a plus suffix to quantifier, additional plus suffix in case of Kleene plus. And it would not only be greedy, but would not give up its captured value during backtracking. Note possessive is not widely supported, so make sure it's applicable to the platform you're using it on. Let's take an example. So dot static foo would match foo hello foo entirely, right? Dot static question mark foo would only match the first foo because it's lazy. And dot static plus foo would not match anything. One second, I need to change it. Yeah, it would not match anything because dot static consumed the entire sentence. So if I remove this part, so it matched the entire sentence in the first pass and won't give up any character back to backtracking. So there aren't any characters available to match foo when the foo part is evaluated in the regular expression. Alright, here's the parsing teaser for you all. This regex would match everything in the input string except the lorem possum part and can be used to strip off all markup from the HTML or XML document, leaving behind only the content. Can you figure out why it only works with a lazy quantifier here and fails with the active one? Well, I won't be explaining this one and encourage you to try in Regex 101 or any test website of your choice until you get it. You will never forget where lazy quantifiers exist and when and where to use them. You can use such regular expressions to do all kind of crazy stuff in text editors like Notepad++, which support regular expressions. Visual Studio Code also has support to search via regular expressions. As an exercise, after you understand how it works, try doing a search and replace operation on this HTML text or any HTML file with this regular expression and see the result. Remember to select radio button for regular expression in Notepad++ and regular expression based search flag, that is dot static, near the search filters in Visual Studio Code to make this work. I'm pretty sure you are well equipped to use quantifier based regular expressions like a pro now. If you like this video, don't forget to give a thumbs up before leaving. And also don't forget to watch other videos of regular expression playlist. This channel has other interesting content like this, so do check it out and subscribe to be notified of upcoming new stuff. Thanks for watching. Bye bye.